All right, I'm going to get started here. This is going to be the walkthrough of homework number 1, and the name for it is A Real Investigation. Okay, so if I'm looking at problem number 1, number 1 says, describe the pattern below using words. So first you're looking at a pattern. And the second step, it says, then draw the next likely figure. So the pattern, if I were to draw it out here, and mind you, I am not the best artist, but I have, for the first iteration, a row of 3 blocks. And then what it looks like is, in the second iteration, looks like I have that same row of 3 blocks, and they're not the perfect shape because, like I said, I'm not the best artist, but you still have that row of 3 on the bottom and 2 on top. And then for the next iteration, there's another row of 3 on the bottom, but now stacked on top of these 2 areas right there, on the left and on the right, we're adding more blocks as well. And then for the last iteration, once again, we've identified this pattern of what's going on. This is a visual pattern that we see, and we're able to look at it and say, okay, so I've went from this to this to this to this. And with each new iteration, with each new block that I'm adding, it looks like I'm adding a block all the way on top of the far left block and a block on top of the far right over there. So the first step, it says describe the pattern below using words. So I can say, all right, well, you're going to start with a row of 3 blocks. And then with each new iteration, add 2 blocks. And where are we going to add those 2 blocks? One on top of the far left block, and the other on top of the far right block. Okay, so 1, I don't have the best handwriting. 2, I'm not the best artist, but I think you can tell by using words, your description, the purpose of this is for you to actually identify the pattern and then describe it using words. So that way you could explain it to someone who maybe has never seen this pattern before and tell them what's going on. Okay, so that's the first step. Second step says, then draw the next likely figure. I think it would be likely that the next figure would stack blocks on top of those 2 right there. So what I'm going to do is I'm going to draw this with 1 extra block, right? You're looking at that and being like, that is awful, right? But I think you get the point. If I had graph paper and I was taking my time doing it, I'd make a nice, neat design. But as you see, it's 1, 2, 3, 4, 5 high, and the same on the other side, 1, 2, 3, 4, 5. Where before we had 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, so we have completed problem number 1. Moving on to the next problem. It says, make a table with a process column to represent each pattern. Write an expression for the number of tiles or circles in the nth term. you're looking at this, you might say, what's a process column and what is the nth figure? I'll explain this. So first, you have your blocks, right? So if I'm looking at this problem, I have a stack of 2 blocks on top of each other, then 4, then 6, then 8. Okay, so first step says make a table with a process column. So what I want to do is I'll say input, and then I'll add a process column, and then I'll say output. All right, so I'll make my column here. So I have my input column going up and down, my process column, and my output. So if you're looking at the first row, right, the output, it looks like I have 2 blocks for the very, very first figure here. And then I have 4, and then I have 6, and then I have 8. So let's just start with that. Let's start with what we know. Okay? And it looks like each time we're adding 2. So we start with 2. So our original process would be 2, and our first input would be the first one, the second one, the third one, and the fourth one. We have our first column going up and down, our second column going up and down, our third column going up and down, and our fourth column. Okay, so what's the process to get it to 2? Well, you could do something like this. You could say 2, because we start off with 2 in the very, very beginning, times n. So whatever n is, my input, in this case, it's going to be 1, 2 times n. So I could say 2 times 1. So 2 times 1 equals 2. And that's where I get that output from right there. And then I go through the next one. So my process is 2 times my input, 2, equals 4. And that's where I get that 4 from. And then I start with 2 blocks times the input, which is 3, and that gives me 6. And then I start 2 times my input is 4, and that gives me 8. Now it says write an expression for the number of tiles or circles in the nth term. So what it's basically saying is, hey, look, these numbers will keep going up. 1, 2, 3, 4. We'll continue to add more columns. The first column, maybe I should have just drawn this out from the beginning, right? But if I had 2 in the first column, and then I had 4 in the second column, and I had 1, 2, 3, 4, 5, 6, and this one I have 1, 2, 3, 4, 5, 6, 7, 8, right? My input each time, this is the very first one, this is the second one I'm dealing with, this is the third one, and this is the fourth one. But if you look at it, the final output of how many blocks there are in this first one, this has 2 blocks in the end. This one has 4, if I'm counting them. This one has 6, and this far one over here has 8. So at some point, you went from, all right, we have the first one, the second one, third one, fourth one. But what if I wanted to find the 158th number in this pattern, right? So if I had like 158, how would I get to find out how many blocks are actually there? So they created this thing called the nth term, right? So I hinted at it at the beginning. And what you're going to do is, no matter what, you're going to start with 2, because 2 is what you have in the beginning over here, right? So 2 times whatever number is actually over here in the n, whatever number it is, you're going to multiply it by 2. And that should give you whatever the process is in the end, whatever this output is. Okay? So if you're coming up with an expression, it says write an expression for the number of tiles or circles in the nth figure. That would be easy. So what you would do is you would take 2 times n, which you've already done, and that would be the output, whatever we've actually come up with in the end. So you might ask yourself, what's an expression? So an expression versus an equation. All right. An expression does not have an equal sign. So I could say like 2n. An equation would look something with an equal sign. So you could say 2n is equal to 10, and then solve for n. So equations, you see they have an equal sign. Expressions do not. So this is an expression, 2n. So your answer here, if it says make a table with a process column to represent each pattern, this right here, everything we did here, would be your table with the process column in the middle. And then it says write an expression for the number of tiles or circles to the nth figure. 2n would be your expression right here. Okay? You could just add it on the very bottom of your process table here, right? They may call it different things. You may call it a process table. In here it says just make a table as long as it has a process column. Okay? So rows go side to side. Rows go side to side. And then columns go up and down. So whenever you hear column, just think of it going up and down. Okay? And that's number 2. So number 3 is similar. Whoops. Let me get rid of that. That is similar. And I'm going to add another layer here and get rid of this one. All right? So number 3 is similar. Current selection layer is hidden. Oh, show. I want to go back and add it again. There we go. Okay, so number 3, if I were to look at it, the same rules apply. It tells me to make a table with a process column, and I have, if I'm looking at number 3, I have 10 circles. Okay, so if I'm making my input, my process, and let's do output. And I'm just making my table here. All right, and input starting off, let's go 1, because I have my first group of blocks. Then I have my second, well, I guess these are like circles. My second group, then I have my third group, and then I have my fourth. If you're ever wondering, like, how do I decide what the input is? This just means that this is the first one I'm looking at, this is the second one I'm looking at, the third, and so on. All right. So if I go on, maybe I'll add this down here, because at the very end it's going to ask me for the nth term. All right, so I have my input, my process, and my output. So let's look and see how many circles we have all together at my output. So in the first group we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 circles. I'm looking at number 3, 10 circles. And the next one I have 15. And the next one I have 20, and then 25. So it looks like each time I'm starting, if I'm looking over here, I'm starting with 5, okay? Then I'm going to add 5 to what I already had. So 5 times n. So I started with 5 in the beginning, and then I'm going to add 5 times n, which in this case is 1, and that should equal 10. 5 times 1 is 5, and 5 plus 5 is 10. Okay, so I put the 1 in that location right there because that was my input. So if I say 5, I start with 5 in the very beginning. Okay, I start with 5, and then I say 5 plus 5 times 2. 5 times 2 is 10, plus 5 is 15, and that's how I got 15. All right, once again, 5 plus 5 times 3. 5 plus 5 times 3. 15 plus 5 is 20. 5 plus 5 times 4 is equal to 25. And then 5 plus 5 times 5. Whoops, I'm already going ahead of myself there. I'm already looking at the nth term. Look at that. So what I'm coming down to here is, if I'm looking for like the 128th or the 522nd number in the pattern, I can just go ahead here and say 5 plus 5 times n, because whatever n is here, I'm just going to substitute that in that place. So at the very end, that's going to be my answer, 5 plus 5n. That's my output. So I made a table with a process column to represent each pattern, and then I wrote an expression. So my expression, remember, not an equation, expressions, remember expressions versus equations. I'm not writing an equation here. An equation has an equal sign. Expressions do not. Okay? So we want the expression. That's what the problem asks me. So my expression is going to be 5 plus 5n. And that's my answer. Okay? So let's take a look at number 4. Number 4 says, copy and complete each table. Include a process column between the input and output. Well, we have practice doing this, so we're going to continue. So if I have input, and I'll just say this is my process, and then my output, I'll go ahead and create my table. All right, so my input, let's say 1, 2, it goes all the way to 6, and then n at the very end. 3, 4, 5, 6, and then n. All right, so it's giving me my input. My output here is 0. I have 1, I have 2, and I have 3. And I'm just writing what the problem shows me. So if you're wondering where I get these numbers from. All right, so how do I get from 1 to 0? What do I do? Well, that's usually, in order to get to 0, I have to subtract 1. So 1 minus 1 is equal to 0. Okay, and my process from 2 to get to 1 would be 2 minus 1 equals 1. So it looks like, and I'm going to try this last one, 3 minus 2 equals 1. Whoops. 3 minus 1 equals 2. Okay, so I want to start with my input and end up with my output. So the process, in order to do that, looks the same among all of these right here. It looks like I'm subtracting 1 from each. So 4 minus 1, 5 minus 1, 6 minus 1. In this case, the process would be n minus 1. So whatever the number is that you had, whatever number was in the input here, you would just take it and subtract 1 from it, and that should give you your answer, right? So we're going to go ahead and do this. I'll go ahead and go back a little bit. Yep. So 4 minus 1, 5 minus 1, 6 minus 1, n minus 1, and say 4 minus 1 is 3, 5 minus 1 is 4, 6 minus 1 is 5, and n minus 1 is finally what I would put. So it says, copy and complete each table, include a process column between the input and output, which we did, and there we go. So I went ahead and completed the table there. Awesome. So I'm going to go ahead here and move on to problem number 5. Problem number 5 gives me another column. So I have my input, my process, and my output. Hopefully, in the beginning, you might be confused and just thinking, what's going on? Hopefully by now, you're starting to get the hang of this input, process, output thing. All right, so I'll go ahead and do that. And I'm going to say 1, 2, 3, 4, 5. Always make these tables a little bit too small. There you go. There's the last one. All right, and I have my nth column. So my output of what I have already, I have -3, -6, -9, -12. All right, so how did I go from 1 to -3? What did I do? Right, so we'll look and see each one. I could have done several things. I could have, I could say, 1 times -3, right? Or I could look at the other ones and say, all right, 3, well, if I could say 1 minus and subtract 4 from it. 2 minus 4 would only give me -2, so that doesn't work there. So if I'm starting and looking at it, say 1, I'm thinking, what are possible ways? I could say 1 minus 4, and that would give me -3, but here's the problem with that. If I say 2 minus 4 and I do the same pattern, that only gives me -2, so I know that's not right. So I have to keep thinking and trying different things. Sometimes in order to find the process, you have to try different things. Let's try multiplying by -3. 1 times -3 equals -3. 2, my input here, right? 2 times -3 gives me -6. All right, I'm on the right path. Okay, so then 3 times -3 gives me -9. 4 times -3, 5 times -3, 6 times -3, and n times -3. All right, so if I'm looking at this, 5 times -3 would give me -15. 6 times -3 is -18. And -3 times n would give me -3n. Okay, that's just an easier way of writing it, -3n. So I've completed my input, my process column, and my output for number 5. Okay, number 6. It says identify a pattern by making a table. Include a process column between the input and output. So we're getting really good at these input, process column, and output. All right, so I'm gonna draw my table here. We're definitely getting enough practice doing this. Like I said, at first it might be kind of confusing, but the more problems you do, the better you'll get at it. And it's given me 2 graphs. Well, number 6 is a graph, number 7 is a graph. We'll do number 6 first. And I have my input, it looks like, is 1, 2, 3, 4, and 5. The directions say identify a pattern by making a table. Include a process column. All right. So let's go ahead and do this. don't know if we're going to add any past 5, but so my output for 1, if I'm looking at it, my output is up and down. There's labels on the sides. I have input on the bottom, output on the left. My output, it looks like for 1 is 2. And the output for 2 is 3. The output for 3 is 4. And then 5, and then 6. So the process of what it looks like here is I'm taking the input and I'm just adding 1 to it. So 1 plus 1 equals 2, and then I get my output. All right. So the main process is just adding 1. So whatever this is, plus 1, plus 1, plus 1, plus 1. 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1. 3, 4, 5, and 6. And I could say that whatever n is, whatever that number is, it could be negative 20 or 522. Whatever it is, I would just add 1 to it, and that would end up being the answer. So my output is going to be n plus 1. I don't think it asked for the nth term for that problem, but I went ahead and did it anyway. All right. The next one, problem number 7. All right. Problem number 7, I'm going to add my input column, my process, and then my output. All right, so draw this like that. And then for input, I have, it looks like 1 through 5. So 1, 2, 3, 4, and 5. And then for my output, if I'm looking at it, it looks like output's going up and down. So that looks like that's at about, I'd say 0.5, like half, right? And then my next one looks at about 1, and then 1.5. 4 is 2, and 5 looks at about 2.5. All right, so as we're going up by 1, it looks like whatever it is we're doing half of, right? So we have like 1, the process of 1 divided by 2, okay, is equal to 0.5, or 2 divided by 2, or 3 divided by 2, 4 divided by 2, 5 divided by 2. If I go through it, it equals 1, 1.5, 4 divided by 2 is 2, 5 divided by 2 is 2.5. And if you can't do that math in your head, you can always use a calculator and type in 5 divided by 2, 3 divided by 2, some of the more difficult ones. All right, so the process would be, for the nth term, whatever it is, you divide it by 2. So, like I said, it didn't ask for the nth term, but I went ahead and did it anyway. All right, no more process columns. Now we got number 8. It says identify a pattern and find the next 3 numbers in the pattern. So I have 3, I have a 6, I have a 10, and a 15, and then it's saying, all right, what are the next 3 in the pattern? If I'm looking at this, I'm saying, okay, I went from 3 to 6, 6 to 10, 6 to 10, and then 10 to 15. How did I do that? Well, how do I get from 3 to 6? I could say multiply by 2, but then that's not the same for the next one, right? So 3 to 6, it looks like I added 3. From 6 to 10, looks like I added 4. From 10 to 5, I added 5. You can play around with it. That worked for me, but you may have said, oh, well, you go ahead and multiply by 2, and that, I don't know, because you're not multiplying by 2 there, so you can backtrack and try something else. Sometimes it's a bit of trial and error, where you're trying something out, doesn't work, try something else. So if I'm looking at this, right, from 15 to the next number, I'm going to add 6 to it. 15 plus 6 gives me 21. And to the next one, I'm going to add 7. 21 plus 7 is 28. And the last one, I have 28 plus 8, which gives me 36. So my answers would be 21, 28, and 36. So I'm trying another pattern here. Once again, it says identify a pattern and find the next three numbers. Start with 1, 3, 9, 27, and 81, right? And then I have to guess what are these next three numbers. All right, so from 1 to 3, you can do multiple things if you're trying addition, right? You're like, oh, addition worked last time, so let's try it again. 1 to 3, well, I just added 2. Oh, well, this I added 6. This doesn't look like a pattern that I would be able to recognize, so we backtrack and we say, what could it be? 1, instead of 1 to 3, let's try multiplying. 1 times 3 equals 3. 3 times 3 gives me 9. I think I found the pattern. 9 times 3 is 27. 27 times 3 is 81. 81 times 3, right, if you want to write it out, 81 times 3 gives me 243. Okay, 243 times 3, and you can use a calculator if you really want. 9, 3 times 4 is 12, 6, 729, these numbers are getting big, and then 729 times 3, 9 times 3 is 27, 3 times 2 is 6, plus 2 is 8, 3 times 7 is 21. So 2,187. And these are the next three terms. So each time we still multiplied each by 3, so we found a pattern, we identified a pattern, and we're able to answer the problem. All right, we'll try and squeeze number 10 in on this page right here. It says Jay has a rare baseball card collection. He currently owns 10 baseball cards. I'm just gonna write down. I always like writing down. With word problems, you read it and you lose track of things. So he has 10 baseball cards. Each month he purchases a new card for his collection. So +1 every month. All right. Write a model to represent the number of cards in Jay's collection after n months. All right, so now we're going through this. We're thinking, all right, do we have to create a process table? What are we going to do to make this work? So you know he starts with 10. And then with every month, he's adding 1. Okay? So we could say, we could do a input. I'll just make this small. I'll do input, process, output. Do a small one over here. Right, we could say, all right, so if we're starting keeping track of this from the first month, right, we're taking however many he had in the beginning, 10, plus whatever the month was, whatever month we're adding, because at the end of the first month, if he's only getting 1 new card every month, you know that the output, in this case, the n is going to be 1, so 10 plus 1 is going to be 11. And in month 2, it would be 10 plus 2, which gives you 12. So we could say in the nth month, okay, 10 plus whatever month it is would be the output that you'd put in here. So you know how many cards he has based off of how many months that he's actually been. So the input will always change, but you're able to create a model. The word model, sometimes it'll say create an expression, create a model, create something to show me how many cards Jay is going to have at any given month. So if I'm looking at an expression that would express it properly, at the end of month 1, if I'm looking back over here, at the end of month 1, he'd have 11. At the end of month 10, he would have 20 cards. So the expression will always be 10 plus n. So that would be my model. 10 plus n is all you would need. So represent the number of cards that would work for there. All right. Moving on. So number 11. Number 11 says, write an algebraic expression that models each word phrase. All right, so number 11 says, for more than a number b. In this case, we're using a variable, and this variable we're just calling b. For more than that. So if I say someone is 4 years older than me, I take my age and add 4 to it. So in this case, right, I take my letter that I'm working with, my variable. So it says a number b, and I want 4 more than that. It doesn't say 4 plus b. It doesn't say b more than this. It says a number b, 4 more than a number b. Okay? So you're adding 4 to it. It wouldn't look like this. Here's what it would not look like. You wouldn't say 4 more than b. Do not do that. Do not do that. Please do not do that. All right. Next one, number 12. It says the product. When you hear the word product, think of multiplication. Okay? So the product, you're about to multiply, of 8 and, so we have 8. We're going to multiply it by something. What are we going to multiply it by? We're going to multiply, you could say the product of 8 and 3, you could say, right? And that's what it would look like, but it doesn't say 3. It says the product of 8 and the sum means we're about to add here, the sum of a number x and 3. Okay, so this is my algebraic expression. Once again, expressions are not equations. There's no equal signs. So I have, if I'm reading it once again, the product of 8 and the sum of a number x and 3. So I'm adding x plus 3, and then I'm going to multiply that by 8. All right? So number 13, I could simplify this, right? I could go through and use the distributive property and simplify it, but right now we're going to write it the way it asks me to. Number 13, it says write an algebraic expression that models each situation. This one says, Jenny had $130. She had $130, but she's spending $10 a week. So if you're spending money, that means you're losing money. So like if you're losing $10 a week, right? That would be like the first week. So per week, I'm going to use W as a variable here and say, hey, look, for each week, if it's week 1, you'd replace W with like week 1, you lost week 1, you lost $10, right? Total. And that would end up giving you 120. If I started with week 2, right, and I spent another $10, that would be 10 times 2, which is 20. 130 minus 20 gives me 110. All right, and keep going down and down and down until I made some more money. But I'm only showing you this to show you the importance of creating a variable right here. It doesn't have to be W. It could be any variable you want. You could call that X or Y or A. I just used the W because that reminded me of the weeks. So for every week, it would go up 1, and you would be able to track and see how much money you have. Okay? Hopefully, eventually, they would either spend less money or make more money. So that way, they're not operating at a loss every week. Okay, number 14. It says, Andy bought a new piggy bank and put $25 in it to save her money. So she bought a piggy bank, and then she put $25 in it. Okay? Every week, looks like she's saving money, which is awesome. She adds $1.50 to the piggy bank. Okay? Sorry, I didn't say every week. It says she adds $1.50 to the piggy bank each day, which is nice. So for each day, she's adding $1.50, and then per day, because you're multiplying it per day. So that way, once again, if I were to just model this a little bit, say she started with $25 she put in there, and then every day she adds $1.50. At the end of the first day, right, 25 plus 150 is equal to 26.50. Okay, and let's look at day 2, right? At the end of day 2, how much money is she going to have in her piggy bank? Okay, 150 times 2 is 3. She's going to have $28. So you can model it once again like that with 13 and 14, right? So what you did was you wrote an algebraic expression that models each situation. And remember, in this case, we're representing numbers with variables, so like 10w and then 1.5d, right? You could have also written this like this, and it would be acceptable if you wrote 25 plus 1.5d, right? That's the same thing. The 0 on the end really doesn't matter, but yeah. All right, number 15. All right, actually, you know what? I'm going to go ahead and just add this on the next one, so that way I'm not trying to squeeze it on there. All right, 15. Number 15 says evaluate the expression for the given values of the variables. So I have 4a plus 7b plus 3a minus 2b plus 2a. And then what it's basically saying is, it's saying like, hey, look, by the way, a is equal to -5, so I'm going to have to substitute that in there. And b is equal to 3. So now I'm going to go ahead and I'm going to evaluate this expression. So I'm going to go ahead and substitute these values in. So if I have -5 here, I'm going to go ahead and substitute it in for a here. And I'm going to substitute it in for a here. And substitute it in for a here. All right? Because at the end of the day, this is my problem that I'm looking at, right? And then for b, all the way down here, I'm going to substitute that in for b there and substitute it in for b here. So what this is going to look like, if I write the step out, 4 times a, well, you said a was -5, okay? 7 times b, you said b was 3, plus, let's see, 3 times -5, minus 2 times, what was b? b was 3, plus 2 times -5. Now remember, we have to use the order of operations when solving, right? If you guys remember, PEMDAS, parentheses, exclamation mark, exclamation mark, oh my goodness, parentheses, exponents, multiplication and division, addition, subtraction. Multiplication and division go together, addition, subtraction go together. And we go left to right. So starting off here, if I'm looking at multiplication, 4 times -5, that gives me -20. And then I can just bring everything down. Some of you might think, well, why are you doing all of that? Why wouldn't you just keep going across? It's a good practice to do just to make sure everything gets accounted for. You're not skipping steps. All right, now let's look for the next multiplication. 7 times 3 is 21, so -20 plus 21. And then I'm just going to bring down everything else that I see. All right. It would be tempting to do this right here, this addition, subtraction, but I'm not going to worry about that right now. I'm going to focus on multiplication first. Remember, there's no parentheses, there's no exponents, there's multiplication, division, so it's multiply. Okay, nothing inside the parentheses I can do. So I'm going to multiply, and I'm going to say 3 times -5 is -15. So -20 plus 21 minus 15 minus 2 times 3 plus 2 times -5. All right, and then I'll rewrite all the way across here because my next step is going to be to multiply -2 and 3. -2 times 3 is -6. Okay, and then my last one, 2 times -5 is -10. So I'll go ahead and write that all the way across. 15 minus 6 minus 10. All right, so -20 plus 21 gives me 1. 1 minus 15 is -14. You can use a calculator if you want. -16 minus 6 gives me -20. Okay, and -20 minus 10 is -30. So that's what I come up with in the end, -30 after all that. Okay, so just backtracking here, making sure we understand this. We're starting off looking what's inside parentheses. There's nothing we can do inside parentheses. We're using parentheses in this case as multiplication, because you might think, oh, well, there is parentheses. Well, you're not actually doing anything inside the parentheses. So there's no exponents, so I move right to multiplication and division, and I start from left and I go to right. So I go through each step at a time. Some of you may have skipped steps or just shown what you've done all in one step. I get that, but it's also good to write everything out so I can see maybe where you went wrong, rather than doing something in your head and getting it wrong. All right, so moving on to the next one. All right, the next one, number 16, says, write an algebraic expression to model the total score in each situation. Then evaluate the expression to find the total score. Okay, number 16. It says, in the first quarter, the basketball team made only 8 shots worth 2 points each. Okay, so once again, I'll write it. In the first quarter, the basketball team made only 8 shots. So 8 shots made. And each of the shots, so each shot worth 2 points. Okay, so write an algebraic expression to model the total score. So in this case, I made 8 shots, and I am multiplying by 2 because each shot that I made was worth 2 points. Okay, so that's my algebraic expression. And I could say, it says then evaluate the expression. So what I would do is 8 times 2 gives me 16. So I then, in the very end, get 16 points. That's my answer. Okay, so the basketball team scored 16 points. Number 17. In the last baseball game, there were 3 home runs. There were two 3-run home runs, which means that every single time that they hit a home run, I hit 2 home runs, and each one scored 3 runs. So that gives me 6 runs total. And then it says that 4 hits, and each hit scored 2 runs. So there are 4 hits, and each hit scored 2 runs, which gives me 8 runs. And eventually we'll have to add them together to get the total runs. So we could say something like this. We could say the home runs each scored 3, and then you're adding each hit scored 2. All right, so if we're going left to right, 6 plus 8, and then 6 plus 8 gives you 14. So you would end up with 14 runs in the end. And that's number 17. Number 18 says simplify by combining like terms. All right, so we have 2a plus 3b plus 4a. Now we want to start combining like terms. And you can combine like terms if they have the same variable. A is different from b. You cannot combine 2a you cannot combine 2a and 3b in this example right here. You have to find like terms. 2a, 4, and it ends in an a. So I can combine these two and say, okay, 2a plus 4a, that gives me 6a. But once I get to here, I cannot combine these two because they're not like terms. They do not have the same variables. So whenever you see the word or the phrase like terms, you could say that the terms have the same variable. And in this case, if you look, a and a, so I'm able to combine them. All right, and I was able to combine 2 plus 4, which gives me 6. I cannot combine this anymore, so 6a plus 3b would be my final answer. You cannot combine that anymore. As much as you want to say, oh, well, you know what, 6 plus 3, that's 9, and we'll just add those together, and that's what the answer will be. No, wrong. Do not do that, okay? You cannot combine it. All right, so moving on to the next one, if we're trying another one, we just did 18. We'll do number 19. 19 says 6r plus 3s plus 2s plus 4r. Remember, like terms. So r and r, those are like terms. And then s and s, those are like terms. The phrase like terms. So I can combine, see I underlined r once and r once over here. Okay, so we're going to combine 6r plus 4r. Gives me 10r. Not 10r squared, we just keep the same variable. Then 3s plus 2s, 3 plus 2 is 5, and I just keep the same variable. Once again, you cannot combine these two terms here. You cannot combine the two, so that will actually be my final answer. And that's all you need to do. You can stop there. All right, number 20 is you have a summer job at a car wash. You earn $8.50 per hour and are expected to pay a one-time fee of $15 for the uniform. So you have to pay $15 for uniform. If you work X hours a week, how much will you make during the first week? All right, so I know I'm making $8.50 an hour. And if I'm working X hours, for each hour I work, I'm multiplying it by 850. So 850, if I work 4 hours, it'd be 850 times 4. If I work 10 hours, it'd be 850 times 10. But at the end of the first week, I'm also paying for this uniform, so I have to subtract $15. It's a one-time fee. This one-time fee for the uniform, right? So if I'm trying to figure out how much I'll make the first week, this is a good representation of it. This would actually be my answer. And then you could test it out, right? You could say, all right, so if I make $8.50 an hour and I don't know, I work, let's say you just work 10 hours. Let's go ahead and evaluate this. Well, 850 times 10, that would give me 85 minus 15. And that would give me $60? Yeah. So the first week, you would end up making $60 if you just worked 10 hours. If you worked more than that, then you'd make more money. But the key thing is to subtract that $15 for the uniform. It's a one-time fee, though. All right, number 20. Moving on to number 21. Number 21 says, classify each variable according to the set of numbers that best describes its values. Okay, there's different types of numbers. There's real numbers, there's whole numbers, there's integers. The one thing I want you to realize right now is, it says, I guess we'll read the problem first. It says the number of times n a ball bounces. All right, so if we're going through all different types of numbers, I'll go through that first, right? You'll have, when you first start off as a kid, when I'm teaching my daughter how to count, I'm teaching her counting numbers. Another word for it is natural numbers. Right, so if I'm looking at this and I'm trying to teach her how to count, I don't tell her to start counting at 0, 1, 2. No, I tell her, I say count at 1, 2, 3, 4, 5, and so on. Up all the way till, now she can count in the hundreds. Now she's counting like thousands now. So you start at 1 and work up. I'm not teaching her negative numbers. That's kind of confusing for a little kid to learn how to do. So counting numbers. Then you have something called whole numbers. And whole numbers include all the counting numbers, but they just start at 0 and they work up. So 0, 1, 2, 3, 4, and so on. And then you have integers. And integers are really the same as counting numbers and whole numbers, but you now also include negative numbers. So you start all the way to negative infinity, right? And you can go negative 3, negative 2, negative 1, 0, 1, 2, 3, and it just keeps going on and on and on. So integers can be positive and negative. Now, if you look at it though, there's also more numbers. There's rational numbers. And rational numbers are any number that comes to an end. For example, like 3.5 or negative 2.657, or any number that you can actually write down. What's another good one? I don't know. I'll just say 2 is a rational number. And then there are irrational numbers. Irrational numbers go on forever and ever and ever and ever and ever. Like, I don't know, 7.9 repeating. And the 9s go on and on and on and on. A famous irrational number is pi. When you get older and you learn further into math, you'll learn about e. Or just like, I don't know, I'm just making up a number. I'll say 92.7287632, and then it just keeps on going. And it never ends. Irrational numbers never end. So these are all different types of numbers. 21 asks me to classify each variable. So it says the number of times n a ball bounces. So n, I think in this case right here, can a ball bounce a negative number of times? No. Can it bounce? So we know it can't be, if it can't bounce a negative amount of times, I know it can't be an integer, rational, or irrational. Can a ball bounce 0 times? Yes. So I'll go ahead and classify this as a whole number. And then it says the height from which a ball is dropped. The height. Okay, well, the height can be measured down to a specific number. So the height wouldn't be it wouldn't be a negative number. I'd say it would be a rational number, the height of what it starts at. All right, that's 21. All right, moving forward to number 22. It says graph each number on a number line. All right, what's a number line? There's my line, and I put numbers on it, right? So 0, 1, 2, 3, 4. And if I'm counting backwards, -1, -2, -3. Okay? These arrows on the end of them mean that the numbers go forever in that direction, all the way, like if I were to draw it, go all the way off the screen. It keeps going to infinity, right? This goes all the way, and the symbol for infinity is that. So this goes all the way this way to negative infinity. We're thinking, what's negative infinity? All right, all the way that way. And you could draw your number line starting at any number, but it has to be sequential. You can't just put numbers in random orders on the line. Just like a timeline, it goes from left to right. So if I'm looking at this and it says, graph each number on a number line, and my first number is negative square root of 24, how do I figure that out? The negative square root of 24? Well, what you do is you can type in a calculator and say, what's the square root? What's the square root of 24? And the square root of 24 comes out to be, it says 4.89897, and it keeps on going, and it's an irrational number. And then you got to put a negative sign out in front of it, as we had out in front here. So it goes on and on and on and on and on. It's an irrational number, but I've determined it's 4.8 something, right? Like you ask me what pi is, I say 3.14 something. And then, so if I were to make my number line, right, I know that this number, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, and I'll add a 4. Whoops. I know that this number has to be between, right, -5 and -4, somewhere in the middle here, -4.8, so probably closer to 5. So I'm going to go ahead and I'm going to just like create a point there and say, oh yeah, this is negative square root, whoops, not a negative square root of -24, negative square root of 24. All right, so if you're looking for that symbol, right, you're like, what does that mean? This symbol right here means the square root of. All right, so the second one, number 23, says 2.5. All right, so 2.5, like that. So 2.5 is the same thing as 2.5. So I look for 2, right? And right between 2 and 3, that looks like 2.5 right about there. It doesn't have to be perfect, right? And I'll say, all right, that's 2.5. So I was able to do 22 and 23 on the same number line. If you want to do separate number lines, you can. This up here, what I drew up here, was just showing you what a number line was. And then down here, this was my answer. All right, next up, number 24. Number 24 says, compare the two numbers, use greater than or less than. So if I have 5, and then I have the square root of 22, I'm going to go ahead and write 25 here too, so we can just put them right next to each other. And I have the square root of 75, and I have to use one of the two symbols provided. How do I know which one's bigger? Well, if I find the square root of 22, right? So I could say the square root of 22. I type in a calculator, and it gives me the square root of 22 is 4.69, and it just keeps on going forever and ever and ever, right? So I'm just saying it's about 4.69. That's what those kind of curly equal signs equal or mean. That curly means it's about, approximate. So it's about 4.69. Is 4.69 greater than 5? No. So we want the mouth to open up towards the bigger one. So 5 is greater than the square root of 22. Once again, you need a calculator for this. The square root of 75. All right, so the square root of 75, what does that equal? Type into a calculator. And that gives me square root of 75 is 8.6602, and then it keeps on going, right? So is 8.6602 greater than or less than 9? It's less than. I'm going to open the mouth up towards the 9 and say the square root of 75 is less than 9. All right? And let's keep moving forward. Number 26. Number 26 says, name the property of real numbers illustrated by each equation. Ooh, these are good. I'm going to tell you. So these are three properties, 26, 27, and 28. This is a bit of a repeat from Algebra 1, but I wanted to tell you what each property was. If you guys remember the distributive property, that would be number 26. Number 27 is the commutative property of addition. And I'm going to go back and explain each one here in a second. And 28 would be the associative property of multiplication. So let's take a look at this. I'll explain each one. 26. So the way we know it's a distributive property, we take A times B plus C, and we take A and we multiply it by B, and then we take A and multiply it by C, and we add the two together. The result would be AB plus AC. Okay? So that's a distributive property. We're allowed to do that in math. Someone sat down and named these properties. The commutative property of addition means that you can go ahead, if you're adding two things together, you can flip the order of it. So I can say negative 10 plus 4. That's the same exact thing as saying 4 plus negative 10. And you can put a parentheses around it just to show it's negative 10. But you can just flip-flop them, and you're allowed to do that in math. The commutative property of addition. You can do that with addition. The associative property of multiplication, what that basically means is, if I say xy times z is equal to x times yz, that's saying that if I'm multiplying everything on the left, I can flip and focus my efforts rather than saying x times y. If I were to do that and multiply that first inside parentheses, I'd still get the same answer as if I would have multiplied it y and z first. Okay, so the associative property of multiplication says that if I only have multiplication, I can go ahead and multiply anything first. It doesn't matter. I don't have to go left to right. I can go in any order. That's the associative property of multiplication. That's a bit of a review from Algebra 1. Okay, so I got two more problems. Number 29, it says estimate the number graphed at the labeled point A. So I'm looking at this. We've done number lines. I'm looking at 22 and 23 and looking at my number line up there. I'm saying, all right, so where does this fall, right? If it's between -1 and -2, right, I'm not going to say, oh, well, that's -2.5. That's not right. The answer here would be it falls at about -1.5. Because if I'm looking at the 0 and moving backwards, 0, -1, -2, I haven't gotten quite to -2 yet. I haven't gotten up to -1 yet. So the middle between the two, if I were to take the 2 and try to find the middle, it would be at -1.5. And it looks about there. It doesn't have to be perfect. That's why it says estimate the number. Last one, number 30. Number 30 says 5 friends each ordered a sandwich and a drink from a restaurant. So there's 5 friends. Okay, they each ordered 1 sandwich and 1 drink. Okay? Each sandwich costs the same amount, and each drink costs the same amount. What are two ways to compute the bill? So you could say, all right, you have 5 friends, and each one buys a sandwich. And then you're going to add 5 drinks as well. If they all cost the same, you could do that. Another way, I guess you could say, is 5 drinks plus 5 sandwiches, right? That's another way you could do it. You could change the order of it and you'd still get the same thing, right? If the cost of a sandwich, I'll rewrite it over here. Let's say the cost of a sandwich is $4 and the cost of a drink is $2. I could say, all right, that's 20 plus 10, so your bill is going to be $30. Or I could write that as 5 times 2 plus 5 times 4. That does not change the value of it. So really I'm looking at this, looking at the commutative property of addition, like we talked about. So 5 times 2 gives me 10. This gives me 20, and I still get 30 here. So what property of real numbers is illustrated by the two methods? I'd say the commutative property of addition is what we could use here, right? These are the two possible models that I would use, and you get the same answer. Okay, so the property, I'd say the commutative property of addition. All right? So these are the 30 problems that you've been asked to complete. I've walked through them. If you look past there, it says, well, what do I do next? Well, you submit them. If you have questions along the way, please let me know. I want to be able to help.